This is lecture 11 for Chem 223. Today we'll be talking about iodometric titrations and of course your changing body. So let's start with your body. Are you past 20 years old? Then this is your body now. It hasn't quite crashed into the ground yet, but the writing is on the wall. All right, well, let's first, before we talk about the iodometric titrations, talk about back titrations and direct titrations and what the difference is. So the direct titration is the type of titration that you're most likely familiar with. In this case, we have an analyte, we put it in a beaker, we throw some indicator in there, and then we add titrant to the analyte until the indicator changes colors. Now this really only works if you have some indicator that's either going to interact with your analyte or titrant. You need something that either changes in color, changes in volume, smell, something like that to make a measurement. But what happens when you have an analyte that doesn't interact with any useful indicators? So you have no way of actually changing color when your titration is done. And the indicator also, or you don't have any useful indicators that interact with your titrant either. What are you going to do? Well, in this case, what we actually do is use a second titrant in here that will interact with the indicator. So what's going on here is we have our primary titrant, which will be a standardized solution, and that's going to interact with our analyte. So some amount of our standardized solution will be used up by this analyte, and then we will react whatever is left over of our standardized solution with a second titrant. And then once all of the second titrant, well, once we stop using up all of the second titrant, then our indicator will change colors. So in lab 3, you'll be doing this. For your indicator, you'll be using a starch. And this starch is composed of a long chain of sugar molecules. They have this general form. So this 6-membered ring in here with this oxygen group and all these side groups sticking off with a bunch of OHs, that is the ring structure of a sugar, and starch is just these ring structures stuck together in a really, really long chain. And what these long chains of sugar will do is actually wrap themselves around I3 minus, or actually more properly around I6 units. So it'll have 2 I3 minuses in there. When these starch complexes with the I6 minus, then all the OH groups on these sugars can hydrogen bond to the I3 and I6 minus complexes, and that causes changes in the electronic structures of these species, causing them to turn blue. So specifically, this whole complex has a blue color. And then as we titrate out the I3 minus and deplete it during our titration, we undo these coils and cause the blue to eventually disappear. So when you start the titration, it'll actually be a reddish color like this, and you'll also see these colors a little better in the lab video, but we start with a reddish color, and we actually will start titrating before we add the indicator down to a yellow color. The reason we do this is because if we add the starch indicator too early, then the starch indicator can complex or form more extensive complexes that actually won't titrate away, and we'll be stuck with some color no matter how long we titrate. So we want to deplete the iodine species in our starting solution till they're yellow like this, and then we'll add the indicator. It'll turn it a darker color. If you add enough indicator, it'll be significantly darker than this, and it'll be easier to see. And then you titrate until all of the color disappears. All right, so let's actually look at what's going on specifically in this lab. So in this experiment, you'll first have to standardize a thiosulfate solution. Now, why do you have to do this? Well, because thiosulfate is not a primary standard, so we have to standardize it to figure out its exact concentration. So what we're going to do is make a solution of KiO3. KiO3 is a primary standard. So we'll throw that into a solution. We'll also add some potassium iodide and sulfuric acid in here. Then what will happen here is the IO3 minus, or the KiO3, this will react with the I minus from the potassium iodide to give us 3 I3 minuses plus 3 waters. Okay, and then once we have this all made, we will have a solution with a known I3 minus concentration. We'll take that I3 minus and we will try and prepare a thiosulfate solution with a known concentration, but it'll be off a little bit. And so what we're going to do is titrate it versus this I3 minus solution where we know the concentration. And we will run this titration until we hit the endpoint. And fortunately, with a starch indicator, unlike a pH indicator, with a starch indicator, the endpoint and equivalence point are actually always the same. And so we'll actually know the concentration of our thiosulfate solution really well. Of course, we'll have to do a bunch of stoichiometry to figure that out, and we will go through that in a slide or two. But then, once we've standardized our thiosulfate solution, we're then ready to determine the concentration of vitamin C in our unknown. And so the way this is going to work is we're going to take some vitamin C tablets, crush them up, and take some of that powder, and that is going to be our analyte. So we'll dissolve that in a solution, and then what we're going to do is add some known amount of the I3 minus solution. So this is our KiO3 plus Ki solution, and that forms this I3 minus. We're going to throw this in, and it's going to react with the vitamin C. So this is vitamin C's chemical formula. You'll notice after the reaction, it's got one more oxygen. So we're actually oxidizing the vitamin C. And while we're doing this, we're using up this I3 minus. So this I3 minus is what's interacting with our starch indicator. And so we're actually going to make this in excess. So we're going to have extra I3 minus, and it's going to react with some amount of our analyte. And then whatever is left over of the I3 minus, we're going to titrate with our standardized thiosulfate solution. And once the thiosulfate has completely reacted with the excess I3 minus, our indicator here will change colors. Okay, so let's go ahead now and practice some of the math here. And these next couple of slides should be very useful for you on Lab 3. If you have them open while you're working, it might help a bit. So first, let's standardize our thiosulfate solution. We're going to start by adding 1 gram of KiO3, that's this IO3 minus species, to 50 mils of water. The 50 mils already contains 2 grams of potassium iodide and 10 mils of 0.5 molar H2SO4. Now for these problems, you're going to assume that the KiO3 is your limiting reagent. Why is that? Well, because we're adding the protons in large excess, and we're actually not adding the potassium iodide in excess. We're actually adding less than excess. So you might think that the potassium iodide is our limiting reagent, but potassium iodide actually gets reformed at the end of this reaction. And so it's actually not a limiting reagent. The only thing that is not regenerated or in large excess is our KiO3. And so that's going to be what controls our concentration of I3 minus in this titration. All right, so the 50 mils from above are titrated with a thiosulfate solution. If 35 mils of thiosulfate solution are required to reach the endpoint, what is the concentration of the thiosulfate solution? And you can pause the video here now and try and work through this, and I will then go through the solution. All right, here is how you will work this problem. We're starting with 1 gram of KiO3. We need to turn that into moles of I3 minus because the I3 minus is what's actually reacting with our thiosulfate. Okay, so we take 1 gram of KiO3, divide it by 214 grams per mole of KiO3. You'll notice I'm leaving off decimal points in these molecular weights just because I'm being lazy. but when you're actually working up the lab, keep as many decimal points as possible. All right, now we have this in moles of KiO3. Now we need to convert it to moles of I3 minus. You'll notice there is a 3-to-1 ratio of I3 minus to IO3 here. So we're going to multiply this by 3 and divide by 1 mole of KiO3. And that will give us 0.0140 moles of I3 minus. We'll then take those moles of I3 minus, multiply it by the ratio that we find in our second equation between the thiosulfate here and the I3 minus. So we'll be multiplying it by 2 moles of thiosulfate for every 1 mole of I3 minus. And that will give us 0.0280 moles of thiosulfate. We know that we used 35 mils of thiosulfate, so what we're going to do, find our concentration of thiosulfate, is take the number of moles of thiosulfate divided by the volume we used. Of course, we're going to convert that into liters instead of using it as milliliters. And that will give us a concentration of 0.80 molar for the thiosulfate. Again, if you're working through this math in the lab, I recommend keeping this slide up, either as a video, pausing the video on this slide, or just downloading the slides that I upload to Learning Suite. All right, so now we've standardized our thiosulfate solution. Now let's use that to figure out how much vitamin C is in a tablet. All right, so we have 3 500 milligram vitamin C tablets, and they're dissolved in sulfuric acid. 50 mils of 0.0280 molar KiO3 is added, along with 2 grams of potassium iodide. If 3.15 mils of 0.8 molar thiosulfate solution are required to reach the endpoint, how many milligrams of vitamin C are in the tablets? Okay, so these are the equations we will need. We'll have to remember this KiO3 plus Ki reaction forming the I3 minus. So that's the amount of I3 minus added. We'll have to remember that we're adding vitamin C, and that's reacting at a 1-to-1 ratio with the I3 minus. And so it's using up some amount of that I3 minus we added. And of course, then we will have to back titrate the remaining I3 minus, figure out how much is left over. So what we are doing here is we know the amount of I3 minus we're forming. We know how much is being back titrated. And so we're going to take the difference between this value and this value to find out how many moles of vitamin C are in there. Go ahead and pause the video now and try and work through this. All right, and here's how we will work through this problem. We know we added 50 mils of the KiO3 solution. We know the concentration of that, but we need to know the concentration, or sorry, we need to know the number of moles of I3 minus that are formed. So we'll take the concentration of the KiO3, multiply it by this 50 mils, convert it to liters, and we'll multiply that by the ratio between the I3 minus and the IO3 minus, which is a 3-to-1. So that will give us a total of 0.00420 moles of I3 minus. We know then that it takes 3.15 mils of our standardized thiosulfate, which is 0.8 molar. That means we used 0.00252 moles of the thiosulfate to completely titrate this species. How many moles of I3 minus were used up by the thiosulfate? Well, it takes 2 moles of thiosulfate for every 1 mole of I3 minus that's used. We're going to multiply this 0.00252 moles of thiosulfate by a ratio of 1/2 to find that we used up 0.00126 moles of the I3 minus from our thiosulfate. Now notice we started with 0.00420 moles of I3 minus, and we only used up 0.00126 moles of the I3 minus with the thiosulfate. So where are the rest of the moles of I3 minus coming from? Well, they're coming from a reaction with the vitamin C unknown, right? So the way we're going to find out the moles of vitamin C is we're going to start with our starting number of moles of I3 minus, subtract the number that were used up by thiosulfate, and that will give us 0.00294 moles of vitamin C. Now, why can we say that that's our moles of vitamin C? Because vitamin C is reacting with the I3 minus at a 1-to-1 ratio. So it used up this number of moles of I3 minus, meaning that there is this many moles of I3 minus left over for the thiosulfate to react with. Now then in the lab, you also need to figure out how many moles or how many grams of vitamin C are in a tablet. And so what you'll have to do then is take this number of moles, multiply it by the molecular weight of vitamin C, and that will give you 0.518 grams of vitamin C. And then of course you can convert that into milligrams. Now this math gets a little bit more tricky in the lab because you're not using a whole tablet. In that case, you're going to just be using 200 milligrams of that tablet. All right. And for the lab, normally you'd be given 3 pills for unknowns. You'd immediately record the number of the unknowns. Of course, you're not getting unknowns if you're doing this online. If you're doing this in person, you will get unknowns and need to record those numbers right away. You'll then need to weigh and crush those tablets as best you can with a mortar and pestle that you get from the stockroom. And of course, anytime you're analyzing an unknown, you're going to need to watch for any type of casing or hard material that doesn't crush as well as other things. Make sure it's all crushed evenly. All right, that should help you get ready for Lab 3. And the video for that, of course, is posted on Learning Suite. And good luck with the lab. In this lecture, we're also going to touch on chelation. Chelation is an important topic, but it's not an especially long topic. So I always kind of struggle with where to put it in the lecture. So I'm just going to put it right here. So chelation is basically when we have a chelating group, such as EDTA, which is shown right here. Chelating groups have negative charges or some other functional group that can attach to an ion, a metal ion, and form a chelating compound, right? So this is just a figure from your book. I've spruced it up a little bit by making the nitrogens a little easier to see here. But what you can see happening is I have all these carboxylic acid groups. Notice they're labeled with blue for the oxygens. And for each of these carboxylic acid groups, one of the oxygens is complexing with this manganese here in the middle. And then I also have these nitrogens in my EDTA, and these each have a lone pair of electrons, and those are also going to be interacting with my manganese. All right, and this chelating agent, EDTA, is what we call a polydentate ligand, which means that it has more than one tooth attacking this manganese here. And right here I have EDTA drawn out in a different way where you can see a little more easily the different CO2 groups. And in this form, we actually have the amines protonated. And you can see that each of these guys does have its own pK value, or its own pKa value. So there's a little bit of a tie-in there. But chelating is an important component of chemistry. And in Lab 4, we're actually going to be doing some chelating, where we're going to take iron 2+ and throw in this O-phenanthroline species in here. And the reason that we're going to do this is we're trying to determine the concentration of iron 2+ in some vitamin tablets. And what happens when these two chelate together is that O-phenanthroline has a natural absorption wavelength of 272 nanometers. But when you complex it with the iron 2+ here, those 2 nitrogen electrons get donated to iron, then that affects the conjugation of all of these rings, and it actually lowers the absorbance frequency, or increases the absorbance wavelength here. We get a higher wavelength, and this guy then shows up at a wavelength of 510 nanometers in our absorption spectrum. We'll talk a little bit more, of course, about UV and visible light absorption and emission spectroscopy later, but this is going here because it's associated with chelation. If you have any questions about chelation, feel free to ask, but it's really not a very complicated subject. It's really just organic molecules sticking to metal ions. Oh, it is simple, but it is also really important in real life. So for example, if you ingest poison, they'll often give you a chelating agent that binds to the poison specifically to extract it. And if you'll notice this picture here with these doctors rushing this patient into some place, I put David Hasselhoff's face on there. I point this out mostly because I'm afraid most of you will miss the joke. It's really important to me that you at least know I'm joking about something. Whether you think it's funny or not, it's important that you see the joke. Also, let's say you get your blood drawn for a blood test. They'll often add some calcium in there. And the reason they'll do that is that will cause some chelation with a lot of stuff in your blood, and that'll stop your blood from coagulating. And lastly, a super important chelating agent is the heme group that's found in a lot of your proteins, especially hemoglobin, which transports oxygen throughout your body. So without chelation, you would, of course, suffocate. That does it for the lecture portion of today's lecture. But this lecture does also come with a handout. I will show you that over here on this page. So this is a polyprotic acid worksheet. It just has some practice problems for you to go through. It also has some isoelectric point problems for you to go through. And of course, this handout is also associated with your reading quiz for this lecture. And it has an answer section down here at the bottom. If you have any problems with any of that stuff, feel free to let me know and I will help you out. Good luck.